This session is going to be on Module 2 limits, and it is just an introduction to the concepts that come up. But it should give you a little bit of a start to consider what exactly we're talking about when we're talking about limits and why it's important. We have actually in the lead up, the courses that lead up to Math 31, done some thinking about limits, but we probably haven't said the word. Interestingly enough, back in 20-1, and it's interesting that there's a kind of a tie from Math 31 to Math 20-1, not Math 30-1 here, that we did some work on sequence and series. And within that, we studied, and this might be a while back in your memory, so I will certainly remind you of what we learned back there. And we talked about infinite geometric series. And that was the idea that we had a series of numbers, and from number to number, we multiplied by something. That's the idea of geometric. And then we added all those terms up and we actually got a sum. Okay, so let's just be reminded of. So we're multiplying from term to term. And the idea is that we're going to do it to infinity. We're going to add all of the terms up, which seems kind of odd. So a reminder of the formula. In 20-1, the formula was this. We normally have it, and I know in Math 31, I believe they use the A. Not a big deal, one or the other. I think this is the one that we'll more use in our discussion. A is the first term, and R is the ratio. The ratio. And the S in this formula is the sum. And so this gives rise to kind of the big question for the day. We really have to ponder this because it's kind of odd to wrap our mind around it. Is it logical? Or in other words, can we add an infinite number of numbers and get an answer? Seems very, very odd. Can we add an infinite number of numbers and get an answer? So why don't we look at a couple of examples and see if anything makes sense and anything doesn't make sense. So here are two examples for us to consider. Example 1, we've got 2 plus 4 plus 8 plus 16 plus ... And then our other example is kind of going the other way around. Example 2. We're going to start at 16. We're going to add 8. We're going to add 4. We're going to add 2 all the way down. Okay, so let's just be reminded about how we identify the different pieces of the information. This is the formula that we're targeting, trying to find the sum of an infinite number of numbers, an infinite series. So A is the starting number, so that's super easy to find. It's given to us, looking at us. So A is 2 here, A is 16 here. To find the ratio, you might remember, you divide a term by the term before it. So term 2 divided by term 1, or term 3 divided by term 2. This has to be the same answer all the way through, or you don't have a geometric series on your hands. So we just take a number, say 4, divided by the number in front, and we get 2. Over here, same thing. The R value would be term 2, which is 8, divided by 16, which is a half. And before we blast off into the series formula, we could get a little flavor as to what's happening here in terms of, could we guess what the sum was here? So if you get your calculator out and you just, so I have my calculator right here. So just to kind of indicate what we're doing here. So we could go 2 plus 4 plus 8 plus 16. So we have a sum of 30 there to start. But if we kept on adding, we're multiplying by 2, we'd add 32, then we'd add 64, and then we'd add 128, then it might get too big for us to multiply by, but you can see that now I got 254, I got a big number. Not sure what's going to happen on this first one. If we go to the second one and we try to find a guesstimate of a sum, so clear your calculator off and go 16 plus 8 plus 4 plus 2. Of course, we get to that same number of 30. We're just adding them in opposite order. But now we're adding smaller numbers each time. So we're going to add a 1, then we're going to add a 0.5, then we're going to add 0.25. And you see that it's not going up very fast, 31.75 if I go a little ways. So maybe we're going to see something a little bit interesting happen one to the other. So the first one looks like maybe something sketchy is going, because as I added up, I got to a really large number here. This one seemed to slow down. I was at 31.75. I hadn't finished. It's kind of looking like it was slowing down. So I'll throw these into our formula. I try not to do it with our formula off the screen. So we get S equals A over 1 minus R. Then I can move this up a little bit. So we get 2 over 1 minus 2, which is 2 over minus 1, which is minus 2. That seems like a very odd answer. Minus 2 doesn't even make sense. We'll come back to that in a second. Let's look at this guy. S equals A over 1 minus R. So we get S equals 16 over 1 minus a half. Grab your calculator out. Just be careful you're doing this in your calculator. The 1 minus a half has to be in brackets, or you do the math on your own to get 16 over a half. And you get the sum here to be 32, which if we kind of, excuse me, gaze back at what we had done kind of by extending the series and doing it in our calculator, it was pretty close to the answer that we were getting to. So example 2 looks like it's kind of logical. Example 2, minus 2 is a ridiculous number. And so, of course, you might be asking, oh, why did I get a ridiculous answer out of this? Well, there are certain times and certain values of R that give us an infinite series that we can find an answer to adding all the terms up. And there are certain R values that don't work. Okay, so you may or may not remember exactly what the R values were, but let's go back and look at this big question that we had talked about. Is it logical, or can we add an infinite number of numbers and get an answer? It looks like the answer should be yes, because in example 2, as we added more and more numbers, we got closer and closer and closer and closer to 32. So then we say that we are we're approaching 32, so therefore the sum, if we could do this forever and ever and ever, would be 32. One way to look at this, possibly that might give you a little bit better idea of why one works and one doesn't, is to try to do this graphically, where we do a quick little graph, where down on the bottom is the number of terms. And over here, this is the sum. So we have to kind of find the intermediate sums. So 1, 2, 3, 4. So sum 1 is just 2, the first term. The second sum is 2 plus 4, which is 6. The third term is 2 plus 4 plus 8, which is 14. The fourth sum, etc. You're going to add 14 and 16 and get 30. And so we see that what happens is as we, and I'm not doing a perfect graph or anything, but the first sum was 2, and then it grew, and then it grew, and it grew. And it's kind of got this huge upwards trajectory so that it actually is going to infinity. There is no sum here because you're going to add and add and add, and the number is going to get bigger and bigger and bigger and bigger and bigger. So the graph kind of looks like a kind of half a parabola. It starts to really increase quickly without bound. If we graph the graph on this side, same thing, the number of terms here that we're adding and the sum. Let's have a look at what happens here. So S1 is 16, S2 is 16 plus 8, or 24. S3, I'm just going to get smarter, 24 plus 4 is 28. S4 is 28 plus 2 is 30. If we go a little further though, S5, we're going to add 1. So it's 30 plus 1 is 31. S6 is 31 plus a half is 31 and a half, because every time we're adding something smaller. You see that it starts out pretty high, you know, like if 16's up here. Again, I'm not worried about how beautiful this is. It does rise, it goes to 24 and then 28, but then it starts getting bigger, much more slowly, and it kind of, turns into a bit of a horizontal look. When you have this kind of look about your sum, this is when you're going to actually be able to find an answer, because what happens is it levels out and it starts to approach that number 32, and it never quite gets there. It's kind of a weird thought about it, but it gets so very close to it that we say, if we could sit here forever and add infinitely tiny numbers, we would get the sum of 32. So we actually are able to say that our limit is 32 or our sum is 32. Okay. So, excuse me. So again, going back and looking at this, yes, it is able to be done. What we need to note is the value of R that will allow us to have a sum. So to be able to have a sum, our R value has to be between -1 and 1, or we could say the absolute value of R has to be less than 1. That gives us a sum. We could call that a convergent series. I don't know that we need to know that word, but we'll put that in there. And then if the R is outside those bounds, so if the R is, well, why don't we say it this way? So if the R is greater than or equal to 1, or the R value is less than or equal to -1, we don't get a sum. There's no sum able to be found. And this is called, when we're dealing with a divergent, sorry, not a convergent, a divergent series. I don't think those terms come up very often in our course, but I think it's kind of important that we know those. Okay, so that's the kind of the nigglings. We're getting the idea of what is limits. Why are we adding these infinite number of numbers to try to figure out what's happening? So the next thing that we look at is we look at series of or sequences of numbers and try to decide a couple of other little decisions that get us set up to really delving in and talking about the idea of limits and how to solve some of the different algebraic questions that are thrown at us. Okay, so let's go look at, I'm just getting another piece of the board kind of ready for us here. So over here, let's look at infinite limits and see if we can have a thought on this. Okay, so let's say that I give you this. I'm going to have these numbers: 1, 1/2, 1/3, 1/4, 1/5, 1/6, 1/7. So really what this is the way that we write it in our math course. And I know this is going to be new because this is just a really brief introduction to Module 2, is we're saying, what's the limit of the expression 1/x as x goes to infinity? So what number do we approach if we put a larger and larger and larger number in the denominator? So that's what you see in terms of the series of the sequence of numbers, sorry, that are up there. 1/1, I didn't put the over 1. And then the number underneath is 2, then 3, then 4, then 5, then 6, and 7. And we could go on and on and on, 1/100th, and then ... 1 1,000th. As this number in the bottom grows, the overall value of this approaches 0. So like if you could get this out, I don't know how far our calculator would go, but you go 1 divided by 100, you get 0.01. 1 divided by 1,000 is 0.001, right? So as decimals, this is 0. Whoops, change my pen back. Sorry about that. This is 0.01. This is 0.001, and so on. So this number is getting closer and closer to 0. So we say that the limit as x approaches infinity of 1/x is 0. And this particular limit is one that we want to kind of highlight. I think it might even be on the formula sheet. I think I give you too much information on the formula sheet, but I think that one might indeed be there. And that is super important to realize, that if we have a statement where we have some sort of number, it doesn't always have to be 1 up there, but something up there, and a number in the bottom, and we're looking for the limit as the number, the variable, gets bigger and bigger and bigger, we're going to get the final answer of 0. So let's see how that applies. Again, I'm just sort of trying to get your feet wet on these. You will go and look at this in more depth. So let's see if we could do this question. Find the following limit. And it's gonna look like I'm cranking it up, but I'm gonna show you a little process we use, and you'll see that it actually is not quite as complicated as you might think. So just putting some algebra to this. All right, 2x squared plus 6x plus 1 on the top, and 5 minus 2x plus 2x squared on the bottom. Now, we can't just put infinity in there because infinity is not really a number. And if we do put infinity in there, we'd have infinity over infinity, right? 2 times a huge number squared plus 6 times a huge number plus 1 over kind of the same thing. It just doesn't get us anywhere. So we can't put it this huge number, and we have to look for a little bit cagier way of doing it. So one process that you'll see outlined that kind of helps us boil down to what to do is to divide each term in the top and each term in the bottom, so we're not changing the equality of things, by the largest variable exponent that there is. In this case, it's x squared. So our next step here is going to be that we're going to divide everything by x squared. So we get 2x squared over x squared plus 6x over x squared plus 1 over x squared all over 5 over x squared minus 2x over x squared plus 2x squared over x squared. Okay. And this particular method is going to allow us to simplify some things and then look back at that nice limit that's in yellow up there and apply it and see what happens. So one more step here to get ready. These guys are going to cancel. These guys are going to cancel. We're going to have some simplifying. So let's simplify this and then have a kind of a gaze at what we've got. So we get the limit as x approaching infinity of 2 plus 6 over x, because there's a little simplification there, plus 1 over x squared, all over 5 over x squared minus 2 over x plus 2. Now, interesting enough, you see a 2 on the top and the 2 on the bottom. That's kind of encouraging, kind of cool. Now, how do we apply this limit to this question so that we can finish? Remember, I mentioned a minute ago, it doesn't really matter what the number on the top is. It could be a 5, it could be a 6, it could be 100. Some number divided by a variable that's getting bigger and bigger and bigger in the bottom eventually is going to get to 0. Okay, because that bottom number is going to grow so large that you're going to get closer and closer to 0. So then we say that if we apply this limit, this piece will eventually turn to 0. And this is kind of how we write it, a little arrow through it with a 0. That's going to eventually approach 0. This is going to eventually approach 0. And this is eventually going to approach 0. And so then we get the limit as x approaches infinity of 2 over 2, which is then just the answer of 2. Now, we're not always lucky enough that the top exponent and the bottom exponent are exactly the same. So we're not always going to have it boil down to a number. You might have it boil down and figure out that, oh, we still can't do it, and the answer is still infinity. And you may find that the answer boils down to maybe a 0 following this process. You'll get into doing some questions, but if you follow this guide of dividing the top and the bottom by the highest exponent, then you will see kind of how that shakes out. Okay, as again, I'm just doing a bit of introduction. Another thing that we could look at is what happens if instead of we're doing the limit as we get to the largest number we can think of in the world, what happens if the limit approaches an actual number that we know something about? What might happen? So let's investigate that as another question. So let's look at the limit as x approaches 2 of x minus 2 over 4 minus x squared. And it's always worthwhile, like don't go down a rabbit hole yet, check and see if you can put 2 in there and maybe it'll work. Sometimes they don't do anything weird and you can just put the number in. So let's just check it. So we get 2 take away 2 over 4 take away 2 squared. Oops, that's 0 over 0. That is problematic. We're not allowed to divide by 0. So we got to try to do some work to see if we can get rid of that problem of dividing by 0. Now I've set this question up so we have a bit of factoring that we can do so we can have some simplification happen. So top doesn't do anything, it just sits there as x minus 2. Now, I don't know about you, but I do not like the back term being the squared term. So I do a little reorganizing. So I have minus x squared plus 4. And then I will take the minus out. I'm going to do this in probably more steps than you would. Minus 1 and then x squared minus 4. And then this is a difference of squares question. So, I mean, do let me know if you want any help with your factoring. There is the requirement that you can do some common factoring, difference of squares, your trinomial. And there's one more I'm going to show you here before I finish up this recording on a sum and difference of cubes that you haven't been shown. That it's not too hard. Okay, so we see our factoring is done. We can cancel this because top and bottom are the same. And then we get the limit as x approaches 2 of 1 over minus 1 times x plus 2. Now let's throw the 2 in and see what happens. 1 over minus 1 times 2 plus 2 is 1 over minus 4. So the overall answer here is minus 1/4. So we actually were successful in being able to do a little more work on that by doing some of our lovely factoring. So again, that's something that will come up when you get into the ones where you're not looking at a limit as x approaches infinity, but you're looking at what might happen when you're actually approaching a number. And there's a variety of types of questions, lots of factoring in that section. Now, as I mentioned, there is one factoring type that you haven't yet been exposed to, and not hard, not sure. They took it out of the curriculum a number of years ago. And again, not really sure why. I guess it doesn't come up a lot. And it's called factoring the sum and the difference of cubes. So the question I'll show you is x cubed minus 27. And I'll outline how you do it. And then we'll double check. That's the nice thing about factoring is once you factor it, if you're not sure you're right, you can multiply, right? They undo each other. So we get a bracket with 2 terms to start with. The first term and the second term are the cube roots. So this is the cube root of term 1. This is the cube root. I'm going to do CBRT of term 2, cube root of 2. So we get x and we get 3. And then the sign in the middle is the same sign as the question. So it's kind of super easy. Just take the cube roots, put the same sign in there. And then we use the answers in the first bracket to get the answers in the second. So we square this term. Okay, so it's term 1 squared. And then the last term in the bracket is term 2 squared. Now, just be careful here. It doesn't matter if it's minus or positive, that sign's going to be plus. And then for the middle term here, we multiply the 2 terms together, 3x, with a different sign. Okay, so right here, whoops, my arrow is not very good there. I better make a better arrow. Okay, so we multiply the first and second term from bracket 1. And use a different sign. Okay, so let's recap that. So the first bracket, cube root of the first term, cube root of the second term, same sign as the question. Then you kind of don't look at the question. You look at the bracket. You square the first term in the bracket. You square the last term in the bracket. Those are the outer terms of the second bracket. Multiply them together, change the sign for the middle one. Now, the loveliness of factoring, because I do like the predictability of being able to verify answers, it's lovely, is if we multiply it back out, we should be able to verify and be super confident we have the right answer. So we'll just do our FOIL here, x cubed plus 3x squared plus 9x. So that's this times this, then 3x squared, 9x. And then do the bottom, well, I did on the bottom, minus 3x squared, minus 9x, minus 27. And beautiful, things cancel, and we verify that our answer is x cubed minus 27. So that short recording is just to kind of get you niggling and thinking about series, infinite series, a little bit of review here on a new factoring method, and a little bit of work with limits. So I hope that was helpful.